Hello, my name is Colt Correa. I work for Intrepid Control Systems, the company that brought to you Automotive Ethernet, the definitive guide. And this presentation is on SOME IP. SOME IP stands for Scalable Service-Oriented Middleware over IP. And as the name suggests, it works over Internet Protocol, either IPv6 or IPv4. TCP or UDP could be used, but UDP is preferred. The reason is TCP has retry and timeout mechanisms that can be difficult for real-time control. As mentioned, therefore, UDP is preferred, and in a single UDP datagram, we can achieve up to 1,400 bytes in a SOME IP payload. So if payloads can be kept to under 1,400 bytes, UDP is preferred. For payloads longer than 1,400 bytes, there is a SOME IP transport protocol available that's designed to be more lightweight and avoid some of the real-time communication problems that TCP has. SOME IP-TP avoids those. The motivation for creating SOME IP is to create a protocol that supports the real-time transport of complex data structures, arrays, and other data elements that are much more complex than what we see typically transmitted over legacy networks like controller area network or FlexRay. Additionally, SOME IP offers a service-based architecture. That means different electronic components of the vehicle can offer functionality or services to other parts of the vehicle that can subscribe or unsubscribe dynamically. This offers a much more flexible and configurable as well as scalable electronic control system because things can happen in real time, as we'll go into a lot of examples. And SOME IP's popularity has increased recently because it's a good protocol that can support the functionality that's needed for software-defined vehicles or zonal architecture. A central aspect of a software-defined vehicle is having a central compute module that contains most of the software, most of the intelligence for the vehicle. And here is where most of the decisions are going to be made. However, distributed throughout the vehicle, you have the actuators and sensors involved in the mechanical action of the vehicle, like opening the doors, rolling down the windows, adjusting the seat, turning headlights on, different lighting controls, and so forth. So this means that in a software-defined vehicle, since most of the decisions are made with the central compute module and actuators and sensors are remote from that the control happens over the network through network communication. And SOME IP supports this well. So we're going to try to describe some of the types of communication and real-time control that SOME IP is designed to support through some examples. The first example would be a smartphone contact list. So let's assume we have a smartphone in the vehicle, and most vehicles these days have the ability to consume over Bluetooth, which is not part of SOME IP, a contact list from the phone. That is a list of names, numbers, addresses of people that you may want to call or the driver may want to call. And normally that data goes into what's called a center console module. But the center console module may not always be the best place to display that information. So for example, the instrument cluster is directly behind the steering wheel and almost within direct line of sight of the road. Therefore, it's safer to display names or anything on the instrument cluster than something that would take the attention of the driver away from the road. So most vehicles have the ability to navigate through a contact list using steering controls and the instrument cluster. So how does this happen? If the center console is storing the data, it has the ability to offer what's called a service of a contact list to the other parts of the vehicle, like the instrument cluster, for example. And this service would contain fields. The fields of this service is really the data that we want to exchange. And in our particular case, the data would be, or could be, an array of structures where each element of the array is a single contact. And then a single contact could have parts of the information being text-based information, could be a number-based information for the phone number, as well as other things. So it can be relatively complex data. And here's an example of some of the types of data that we're able to work with SOME IP. Here we have an enumeration of C-type. That would be the type of number that we're storing, mobile, work, or home number. We can see that we have several structures here. Structure of a phone number could contain both C-type, what type of number is it, and then the actual character array of what the number is. This could also be a number array as well. Contact would be the first, last name, could have an age in there, and then also include the struct of the phone number. And then a contact list could include an integer of the number of contacts stored in the structure, as well as an array of structures that includes the contact and then the max number of contacts that the device can store. So you can see here that we have nested arrays, we have nested structures, and all this type of data can be transferred over some IP. And this type of data is very different than what we typically see on legacy networks like CAN and LIN, FlexRay, where we're just transmitting sensor and simple scalar sensor and actuator information. We should also keep in mind that the contact list could change in real time. So let's say a different person came into the car after a contact list was consumed by the center console module. And this new phone that's in the vehicle is the preferred phone. So what might happen is the contact list could actually switch over from one list to a new list. Or you might take your phone out of the vehicle and not even have a contact list at all. So having the ability to have a service of a contact list doesn't even make sense. So some IP offers flexibility not only in its ability to transfer complex data types like we've shown here, but also to dynamically adjust for the real world conditions that are happening around the vehicle. For example, one phone is gone or another phone comes in that's a preferred phone. You can make these adjustments. So the services in some IP can appear and disappear based on the conditions of the vehicle. And all this is done without any software changes to the vehicle system. Some IP can also be used to dynamically adjust for different configurations of a vehicle. So for example, you might have one vehicle type that has 5 different radio options. And each radio option could have different types of functionality and offer different services than the others, or slightly different. With some IP, the different radios can publish what services they offer, or other components of the vehicle can search and try to find services that the radio offers. And if it doesn't offer a particular service because of the configuration type or the type of radio that it is, then the rest of the vehicle can make those adjustments in real time, and again, making these adjustments without any software changes to any of the components of the vehicle. So you can see that some IP offers the ability for different vehicle configurations with different options, different components that offer different types of functionality. In other words, different services can be put together, and dynamically the different components of the vehicle can figure out what's available, what's not available, and make the appropriate adjustments and work together with no software changes. Another good example is a radar system. In our example, we have a forward-facing radar and a rear-facing radar, and these radar modules have an output that includes object detection information. And so you can see here that we have a structure, it's called radar data, which includes which sensor the data came from, number of objects that are stored within an object array, and the object array is an array of a structure. And you can see here that's objects, which could include a range, a velocity, angle, and so forth. And then we have a vehicle radar network, which includes a number of sensors, the number of devices, and that could also include radar data with the maximum number of sensors. So you can see here again structures and arrays of structures being used. And the interesting thing about the radar system is that just like in the cell phone case, radar systems can become functional and non-functional based on environmental conditions. So if you're driving in the wintertime in a cold climate and snow gets packed into the front of the radar system may go from functional to non-functional while you're driving the vehicle. And the rest of the control system then would have to make adjustments for that system no longer being able to provide data. So in our example, the radar modules provide a service that includes radar data. They might also include information about radar status, and also may include fields or parameters that can be sent to the radar system to control the radar sensor itself. So this would be an example of the radar module offering a service to the central compute module. And the central compute module then consumes the radar data, consumes the radar status information, and can remotely control the radar module. Okay, the last example that we're going to go into a little bit more detail as we go through this presentation is a mirror service. And this is loosely based off of a real-world application of a zonal software-defined vehicle architecture. So what we have here is we have a right mirror module. We have, of course, a central compute module, and attached to the central compute module is a screen or a user interface. And the central compute module then in this case will offer a mirror button service or user input for the user to control the mirrors in the vehicle. So in this particular case, the central compute module offers a mirror button service to the mirror module, where the mirror module will monitor that information and make adjustments to the mirror module. And the other way around, the mirror module will provide a service to the rest of the system to provide mirror fold status as well as mirror position in a service. So that's kind of the overview of what we're going to go into more detail as we move forward. But this is just another example of how we can use service-based architecture or some IP to control different aspects of the vehicle. Okay, we're going to go into a lot of detail about how this control works, but before we do that, I wanted to give an overview about the specifications of some IP. The most recent specification for some IP is within the AUTOSAR family of specifications. And AUTOSAR is a big topic for real-time embedded systems for automotive applications specifically. We don't have time to go into all of those details, but some IP is compatible and can be used on top of AUTOSAR, but it should also be noted, and it's important to understand, that some IP does not require AUTOSAR, does not require an AUTOSAR ECU or AUTOSAR stack to function properly. So some IP, the basic protocol specification is what's called protocol specification. And in there we have our message format. We're going to go into the detail of this. How to serialize data structures. It goes into some detail, not complete detail, but it also talks about how to use some IP with UDP and TCP, the limitations, and also error handling. The next specification that's optional is the transformer. And the transformer goes into a lot of detail about how to transform memory data, structures, scalars, arrays, bit fields, unions, you name it. All of this is defined how memory format of a processor can be transformed into a wire format on the wire, how to transmit the actual bits, and then on the receiving end, how to take the wire format and transform it back into the memory of the receiving ECU. So that's the IP transformer. Should be noted that some IP transformer can be replaced and is replaced in practical applications with other types of serialization technologies. And the one that I see used most often is Google protocol buffers. So this presentation, we're not going to go into Google protocol buffers, but it's something that you can check out, and there's lots of help and videos on that. And I see widespread use of Google protocol buffers throughout the automotive communication industry, especially on top of Ethernet. And then we have what's called service discovery. Service discovery is what provides the ability for the system to discover services dynamically. So this means that on boot of an ECU, it can publish, it can send out information. These are the services that I offer. Or on boot an ECU, you can ask the system, what services are out there? I'm looking for this service that I need. Is it out there? And then the service provider can then respond with information on how to connect that service how to connect and get data from that service. So that's service discovery. It does say service discovery is optional, but service discovery, as far as I have seen, has been ubiquitous or used in almost every some IP application. And then we have the some IP transport protocol. Some IP transport protocol, again, is optional and is designed to transport payloads larger than 1400 bytes. So in a single UDP datagram, you can transport up to 1400 bytes. So if your data is less than that, then you don't need any type of transport protocol. You can just send everything in a single UDP datagram. But longer payloads require some type of transport protocol. TCP is discouraged because of its timeout and retry mechanisms that don't fit real-time control, and designed as a replacement for that is a transport protocol. So we'll go into quite a bit of detail of both the protocol specification, detail into the transformer, service discovery, and transport protocol as we go through this presentation. Here you can see how some IP integrates in with an AUTOSAR stack. We have the basic some IP as well as service discovery that both connect to standard socket adapter from AUTOSAR. And it should be noted that the some IP uses the same PDU router that AUTOSAR uses. So this is very convenient for getting PDUs or data items in and out or communicating across the network in a standard way, the same as the rest of AUTOSAR. Some IP can be used in both classic and adaptive AUTOSAR. So whether you're using Linux or not, it is supported. Another important thing that AUTOSAR provides is what's called an AR XML file, or an AUTOSAR database file. And this is an XML format that contains a description of, or can contain a description of an entire network, including all the PDUs that are on the network, which ECUs are on the network, nodes, which ones transmit, which ones receive, what PDUs are received or transmitted, as well as all information about some IP, including IP addresses for the nodes and which PDUs come and go for what some IP services. So it's a full description, a very complicated file that can describe nearly everything on a vehicle network, including legacy information like CAN and FlexRay information as far as signals. The same information that you'd find in other legacy databases like DBCs or in FlexRay 5X files can be found also in an ARXML file. And Intrepid does have an ARXML file database editor. It's called EEACOM, and you can find out more information at this link here. This is a tool that will enable you to create and edit ARXML database files for a wide variety of purposes, not only some IP, but for any type of ARXML data. A few times throughout this presentation, we've discussed the word service. So what is a service? A service in the context of some IP is an abstract concept. A service is a combination of any number of, including 0, events, methods, and fields. And events, along with event groups, is anything that can happen cyclically or on change from a provider to subscriber. So what happens is in some IP, a subscriber subscribes to an event group that contains one or more events, and when the event trigger happens, data is sent from the provider to the subscriber. And when we say an event trigger, the trigger could be anything. It could be periodic based on a timer. Could be, for example, when a door opens, windows roll down, when a phone goes in the car and consumes a new contact list. The data that's sent is a field, and a field could be any type of complex data that we've discussed already, arrays, structures, and so forth. And fields can also have getters and setters. Getters and setters are a remote procedure call, or RPC, that can either get the value of a field, again it can be complex data, or set the value of a field. And a notifier is just a term for the concept of sending data when new data happens on change. So it's essentially the same thing as an event group concept, but just when data changes, you get notified that there's new data. Method is a remote procedure call for any action that you want to happen on the provider side. So the subscriber can invoke any action that through methods on the provider side. So this might be reset, for example, reset the contact list for the phone to clear it out. Could be unlock the doors. Could be run a particular diagnostic test. There's lots of examples of methods. Okay, let's get into the nuts and bolts of how this works. As previously mentioned, in some IP, you have consumer ECUs and provider ECUs. Provider offers a service, and within a service you have optional fields, and fields can optionally have getters and setters, and also the service can have optional events and event groups that can be subscribed to. We have optional methods as well that can be invoked remotely. On the consumer side, it subscribes to a service, requests event group notifications, receives notification events from those event groups, and can invoke the methods get and set on the provider side, and can also send a request and receive a response via methods. Keep in mind that consumer ECUs can also be provider ECUs, providers can be consumers, and data exchange between the consumer and provider can be simple or complex. So in here we represent two different ECUs where ECU A is a consumer for a particular service and ECU B is the provider. Each must have its own unique IP address, and data exchange happens on a specific port as well, because we're going to use something like UDP to do the communication, either UDP or some IP TP. Should be understood though that the consumer of a service can be more than one ECU. So on the consumer side, you can have a single provider that sends data to multiple consumers, and we'll go into that in a little more detail when we talk about multicast IP addresses. Here's the type of communication that can occur on some IP. First, we have a method call. The first example here would be a method call with a return, where the consumer makes a request with optional parameters to the provider. The provider then would provide a response with optional results back to the caller, which is the consumer in this case. Then we also have a type which is called fire and forget, that is without a return, where you just make a request with optional parameters and just assume that things worked out well. And we also have getters and setters. A get or a set with optional parameters would be sent from a consumer to a provider, and then the response can come back with optional results. And these parameters and results that are mentioned here throughout this slide can be simple data types all the way to complex data types that we've discussed before: arrays, structures of arrays, arrays of structures, and so forth. An event group notification looks like this. Here we need service discovery. So at the start we would use service discovery for the consumer to subscribe to an event group in the provider ECU. Then the provider would send an acknowledgement that this subscription was successful. And then we would get notified whenever that event group trigger occurs. So the event group triggers could be anything, like if you're subscribing to a Windows service, for example, to roll up or down the windows. The event of driver pushing a button to roll down a window could be a trigger to send data. Triggers can also be periodic. You can say send this data every 10 milliseconds or 50 milliseconds. Triggers for event groups to send data can be anything. But once we subscribe, essentially anytime the trigger happens for an event group, we would get a notification that contains the field data for that event group. And then we would get the results whenever the triggers occurred, which could be periodic or not. Field notifications are very similar. We use service discovery to subscribe to an event group, and field notifications are essentially very similar to event group notification. Difference is that field notification sends results whenever the data for the fields is modified or changes. So then we would get these results whenever the fields that consist of the event group, that are inside of the event group, change in value. The IP in some IP stands for Internet Protocol. An Internet Protocol is going to be used to provide the capabilities of routing and addressing traffic to the right participants. First thing to understand is service discovery in some IP requires a multicast address, and that multicast address space must contain all of the ECUs that are going to participate on a some IP network. All of the ECUs that need service discovery capability need to be part of this multicast address space. So if an ECU wants to publish the services that it provides, it can do so on that multicast address. If an ECU wants to find a service, it can do that on the multicast address. And if an ECU wants to subscribe to a service, that also requires a multicast address of all of the ECUs on the network to be able to do that. Additionally, it is possible for event group notifications, field data, to be sent from a provider to multiple consumers. One way for this to occur is with a multicast address space. So in this particular case, we can have a subset of the participants on a some IP network be part of a different multicast address space than the service discovery address space, and this address space be used so that a single provider can send to multiple consumers. So the configuration of the IP addresses, the ports, the multicast address spaces must be carefully considered, and configured properly for a some IP network to function. But once it's configured, then the IP capabilities with multicast and unicast addresses takes a lot of the burden, the heavy lifting, away from the software inside of the ECUs that are participating on the some IP network. We can just rely on Internet Protocol capabilities to do most of the addressing and routing for us. Okay, now we come to the actual details of how things happen on the wire. Some IP header format is presented here, and this is used for all some IP messages. It should be understood that bit 0 here, right at the start of the header, this is the start of the UDP payload. So before this is a UDP header, and before this is an IP header, but we've already covered details about that. We're not going to go into that and just assume that it is understood this is the part of the UDP payload. So what we have first is a message ID, and a message ID consists of a service ID, which is 16 bits, and a method ID, which is also 16 bits. Now, should be clear that service ID has to be globally unique for some IP. Normally it would be the entire vehicle, but you could theoretically have some IP on one VLAN in a different domain of some IP on a different VLAN. So as long as the traffic's completely separated within a vehicle, within, let's say, a some IP domain, this has to be globally unique. And then we have a method ID, which is 16 bits from 0 to 7FF. If the value is between these two, 0 to 7FF, it means it's a method. And if it's above 8,000 hexadecimal, then to 8FF, then these are events or notifications, more accurately event groups. And then there are some special use values, which we'll talk about. 8100, which is for service discovery, and then 8000 is a magic cookie for special purposes. So the length is a 32-bit value that covers from the request ID all the way to the end of the payload. The request ID consists of a 16-bit client ID, which distinguishes multiple calls to the same method from multiple clients. So you might have one provider that is servicing multiple subscribers or multiple consumers. And a session ID distinguishes multiple requests from the same client. So you might make multiple requests in succession, not get an answer, or have your bytes in flight, and the session ID would be the way that you could distinguish between multiple calls from the same client. This is optional, the session ID. Then we have a major protocol version for some IPs, currently 1. There's no other number. If there's some incompatibility with some IP. In a future version of some IP, this might change, but as of right now, it's just one. And then we have an interface version, the version of some IP service interface. So this would be decided by the person implementing the service. And then we have, so that's the protocol version, interface version. And then we have the message type, which is an 8-bit number. And a message type is, for example, a request with no return, event notification, response, and then we have an error condition, and then we have some other ones that are, we're going to go into a little bit more detail, which are for the some IP transport layer. So that is the message type, and then return code. So return code could simply be just EOK, no error occurred, not okay, unspecified error, and this is not a complete list. Not ready, malformed message, these types of return codes. There's a full table in the specification. So that's the header, and then right after the header we have the payload, and then in the payload is going to contain our field information or the parameters that we're going to send into a method. That's the start of the payload, and we're going to get more detail of what this payload looks like when we talk about the some IP transformer. Okay, so let's discuss our real-world example. So what we have is a software-defined vehicle with the zonal architecture, and in there we have a user interface, could be a touch screen or some buttons, connected to a central compute module. The central compute module is going to be the main brain performing most of the decision-making in the vehicle, and we also have close to the rear view mirrors, a right and left mirror module. So this mirror module can control the I/O of the physical I/O of the mirror itself. So one way that we can implement service-based architecture for this example is to have a button status service inside the central compute module that provides information about the status of what the user is doing with the user interface. And on the mirror module side, we could have a service that provides status of the mirror position, as well as whether the mirror is folded or not, and whether there's an error state happening in the right mirror module. The button status service needs a service ID, as all services do. The number is somewhat arbitrary, as long as it's globally unique within the some IP domain. It's okay. So in our case, we assign a hexadecimal 20 to this one, and the mirror status service, we do service ID of 10 hexadecimal. And then we also need an instance ID. Instance ID is also somewhat arbitrary, as long as it's unique per service ID. So instance ID, we just assign 1 here, and we assign 2 here, but this could have been 1 because this is a different service than here. Then we have some fields. I'm going to explain the fields first by looking at the enumerations and structures that the fields consist of. So this is an example to show that we have some non-trivial data types. So in this particular case, we have a structure that's mirror position. So we have a struct that's called, the name is mirror position. And what it is inside is assigned in of the x, assigned int 8 of the y position, so this would be the x and y position of the mirror, and then also fold position for the mirror f. This fold position then is an enumeration. This enumeration is 0 means that the mirror is folded, 1 means the mirror is open, and 2 means there is some error state. Then we also have an enumeration of button position that are used in some of the fields. And the button position is 0, 0 off or error, just like the fold position, and the button position would be the user input, meaning either off means not pressed and on means it's pressed. So now that we've explained these data types and this structure, we can see here we have fields of button position, mirror button up, down, left, right. That would be fields provided by the central compute module, and the field that is in the right mirror module is simply just a mirror position. So mirror position would be position of x, y, and fold position. So those are the fields. The event group then could be associated, event group would be associated with certain events, and in our case we would have these events associated with this event group. Could be all of them at once. And if we associate all of these events to this event group, it means that whenever any of these events fire, then this event group trigger will be, the condition will be satisfied and will send data if someone is subscribed to that this event group for notification. So that's one way to do that. So these events are button up, button down, button left, and button right. So those are just different buttons for the user to provide input on how they want the mirror positioned. And in this case, we have the events mirror fold position, mirror X position, mirror Y position. This could be sent whenever there's a change in data to a subscriber. And also in the mirror service, we have two methods for get mirror position and setting of the mirror position that the central compute can use to control the position of the mirror. So once we've assigned all of our IDs and have the structure set up, the rest of the work is relatively simple. It should be noted that this information, service ID, instance IDs, fields, and so forth, are all defined within the AR XML file that I described earlier, and we have the tool EEACOM where you can look at that. So EEACOM is or something that enables you to look at the AR XML file as something that's an important tool to be able to understand how architecture of some IP works. So as we move to the next slide, we should remember some of these things because I'm going to show how all of these things fit into the message structure of a SOME-IP message. Okay, what we have here is the message structure that we went through earlier and our example. So let's go through a couple simple examples. Let's say that we were a client that wanted to call one of these methods, set mirror position. So what we would do is set the service ID to the service ID of the mirror status service, which is 10 hexadecimal. And the method ID would be the method that we want to call, in this case 31 hexadecimal for set mirror position. And then the length would be the length of the header plus the size of the mirror position structure, which is here. The client ID and the session ID would be the client ID of the caller, and if you want to have a session ID, that is, know which return matches this call, then you can add in a session ID. This is optional, it can be 0. Then of course we've discussed the protocol version, interface version, message type, which would be a method call, return code would be ignored in this case, and then finally we'd get the payload, and right at the payload we would have the serialized data of the mirror position. And the serialized data of the mirror position will cover how that works when we get into how the SOME-IP transformer functions. And let's do another example. Let's say that the button status service wants to send an event notification of the mirror button status event group. In this case, the button status service would put the service ID as itself, which is 020 hexadecimal. The method ID would be the event group ID, which is 1850. Length would be the same thing, the length of the header plus the payload, which is in this case would be these event field data added up together, which would be right here. Client ID would be the client ID of the subscriber, and session ID would be 0. We have the protocol version, interface version, and then message type would be of type notification, and then return code would be successful or 0. And then finally at the payload you would have the data mirror button up, mirror button down, left and right as a set of data for all of these events. And keep in mind that the event group or data within an event group is defined at design time. So we had defined that mirror button status event group contains all of the fields for all of the buttons up, down, left, and right, just by definition at the design time. Could have done it differently. Okay, so now let's talk about the SOME-IP transformer. The SOME-IP transformer is a set of rules that enable an ECU to take memory data, could be complex memory data of structures, arrays of structures, scalars, you name it, and transform that into a serialized format that is sequential in nature, that can be transmitted on the wire on Ethernet, then received by a receiving ECU, and then the methods and rules of how the receiving ECU can unpack the information and put it back into its memory. Now, this is exactly what for some IP messages will be right at the payload. So this tells you how to transform your memory information into a serialized format that will get put into the payload of certain some IP messages. That's what a transformer is. Before we get into the details, I should note that in real-world applications, we do see the some IP transformer used, and also other transformers, like, for example, Google protocol buffers. And I've heard discussions around the advantages and disadvantages of both. That'll have to be taken for another presentation since we don't have time. But in general, one very important thing within transformer that must be considered is the amount of processing power it takes for this transformation to occur. It is often non-trivial, and sometimes, if the transformer is not done properly, can lead to very heavy processing load on processors to just be able to transform this information from a serialized format to memory format and back and forth. So it is non-trivial amount of processing that this requires, and should be considered carefully how much processing power is taken for different types of transformers. And the some IP transformer, in the simplest form, is designed to have minimal impact on processing power. So in the transformer, there is a lot of different options that can be used regarding padding, alignment, tags, and many other attributes that we won't have time to go into today. And this is defined in at design time. And the rules, so for example, alignment, how do you pad things, byte order, and such, are all defined within the AR XML file. So we have basic data types, which includes Boolean, int8, unsigned int8, all the way up to float 64. These are the scalar simple data types. And then we also have strings, arrays, multi-dimensional arrays. The transformer talks about how multi-dimensional arrays are supposed to be transformed into wire formats, enumerations, bit fields, unions. So we won't have time to go into all of the different details of all the data types and the rules. Depending upon the actual hardware that's being used, which processors, you might want to implement different types of alignment strategies. So for example, some 32-bit processors or 64-bit processors, if memory is aligned on a 32-bit boundary, makes them much more efficient. So this is an example of how we might align different data types. So for example, if you have a 32-bit alignment, you have a uint8, so an 8-bit number, then you just put the 8-bit number and allow padding for the rest of the values. So there's lots of rules, and the implementation really depends on the application, which processors are used, how the software is structured, and there's lots of, as mentioned, rules around how this can be done, and how it's done is all defined again within the AR XML file. The transformer for some IP also includes an option for what's called tags or tagging. And tagging is a method where you exchange more complexity and bandwidth for flexibility in implementation, especially compatibility between old and new versions of software. So let me try to explain. What we do with tags is we put additional information beyond just the data into the serialized format. And what that does is that allows the receiving ECU to interpret the data based on what's transmitted and not assuming that it's in a specific fixed format. So what this allows for is more flexibility and specifically more compatibility on the ECU software versions. So what this enables you to do potentially is have a new software version inside of an ECU that does not affect older versions of software and other ECUs that still need to communicate with the new ECU. And as we go through this example, I'll try to explain that in a little more detail. So first we put in a wire type. So in other words, what type of data is this? For simple data types, we just have a size. And for more complex data types, we have several options. First is a complex data type with a static size. In other words, we're not going to transmit the size. A complex data type with a 1 byte size. In other words, the size is up to 255 bytes. Complex data type with a 2 byte or 4 byte size. If we are transmitting the data with a size or a length, then we would have a length field here. If we're not, then this length field will not exist. The next thing after wire type, we have a data identifier. This is the specific tag. So the data identifier would be unique for the particular data that we're transmitting. So the receiving ECU would look at this ID and say, hey, I know exactly what this data type is based on this data ID. And if the receiving ECU does not recognize the data ID, then it can just ignore this section. So you can see how the data ID provides a way for receiving ECUs to consume data that they recognize and ignore data that they don't recognize, and makes the coupling between the sending ECU and the receiving ECU software versions much more amenable. Makes it easier to control or to decouple the software versions from the receiving ECU from the sending ECU. So as we mentioned, after the data ID, we have a length that is optional and only used for types 4 through 7. And then we get the actual data that we want to transmit. So you can see that the cost of using this type is all of these bytes of data or bits of data right here are all consumed and not used. It's not used to transmit actual data. The actual data is only contained here. So if you want to transmit it in a 1 byte or 8-bit data type, we will consume significant additional bytes on the wire, which leads to less efficiency. But the benefit is we can loosely couple software versions. So this is how tags work, and then essentially after you get done with one tagged member data, then we just put the next tag member data here. So this is just representing the very next data type. So we've just put this one here, put the next one, the next data type, and the next data type, the next data type, and so forth until we're entirely done with the amount of data that we want to transfer for this. Again, another method that is commonly used in automotive is Google protocol buffers. This is another technology that can be used and employed, but my understanding from the designers of SOME-IP is that the SOME-IP specific version is designed to be less processor intensive when compared to Google protocol buffers, but Google protocol buffers are sort of ubiquitous. They're everywhere in internet communication, and they're also heavily used within automotive communication, simply because the infrastructure and the support for them, the capabilities is really high. So that might be something you look into. It's not part of this presentation. Okay, and now we're going to talk a little bit about service discovery. This is how ECUs can publish what services they offer, and other ECUs that want to be consumers of services can subscribe to services and other ECUs. So first should be understood that in order for this to function, we need all ECUs are going to participate with subscriptions and publications. They need to be within the same multicast address space. So we have to define a multicast address space. This is an example with a known port as well that all ECUs will communicate service discovery on. And then we have different concepts within service discovery. First is a find service used for clients to search and discover services that they're looking for. Offer service used by servers to publish what they can do. Then we have stop offer service. So for example, stop offer service, if you offer a service and then later on you no longer have the ability to offer that service, and you can say stop offer service. And this shows the dynamic nature of SOME-IP as we discussed before in our some of our examples, like a radar example. If you start offering a radar service and then you're driving down the road and a bunch of mud or snow gets packed into the radar and it stops functioning, then you can do a stop offer service letting the system know that the service is no longer available. And then we have subscribe event group. This is how we subscribe to events that will send field data. Stop subscribe event group and subscribe event group acknowledge or ACK. Those are the main message communication types that we're going to have in service discovery. Okay, well here's a message flow diagram of how some of these messages can be used. What we have again is a right mirror module and a central compute module. The right mirror module is going to look for a service somewhere that offers the ability to see when the user interface buttons are pushed to adjust the mirror. So that's what we have in our case, and that service is called the button status service. And it happens to be inside the central compute module, but the right mirror module doesn't know that. So the right mirror module could say find service. This goes out to the multicast address space of all ECUs that are participating on this some IP domain. And the central compute module would say, hey, that's me, I have that service, and it would offer that service back to the right mirror module. Again, this all happens on multicast, service discovery. Then the right mirror module would then use the information in the offer service to subscribe to the event group. Now this particular communication is not going to be multicast because one thing that the offer service transports as information is the IP and port of the device or ECU that's or server that is offering the service itself. So once this offer service comes in, the right mirror module then has the ability to know the IP and port of which to communicate to the ECU in order to get the service it's looking for. And then we want to do a subscribe event group. The event group would be, I want to subscribe to the mirror button status event group that contains all the fields here. And then you get an acknowledge if it works properly from the central compute module. Yes, I did subscribe you as an entry, the right mirror module, to send information to you whenever the trigger for this event group is fired. And then we have normal some IP communication that we covered before, that anytime the trigger for the event group is fired, then we send data to the right mirror module automatically. And specifically that data is going to be the fields of mirror button up, mirror button down, left and right. Okay, this is the message structure for service discovery messages. You'll notice that the main header is identical to all other types of some IP messages. That's the yellow part here. We have the message ID, length, and so forth. The difference is for some IP we have a fixed message ID and method ID. FFF8100 means that it's a service discovery message. And the protocol interface message type return codes are also fixed, and some of the other ones are not used. So what's new is instead of a payload, we have some new information here: flags, reserved, length of entries array and entries array, length of options array and options array. I'm going to do my best to describe how this works. So what happens in some IP service discovery is, if you want to publish, let's say you have 5 different services available. When you go to publish services, it is possible that you can publish all 5 with one message with these arrays. So what happens is that let's say you have 5 services you want to publish. You would have the length to cover the 5 services that you want to publish, and then you'd have an array of size 5 entries that would provide information about those 5 services that you want to publish. And subscriptions the same way. If you want to subscribe to 5 or 10 or 2 or 3, doesn't matter. You can send a single message to subscribe to multiple services. And then we have options array. Options array is an array of different types of options. We're going to go into some detail. There are many different options, but There are lots of information that can be provided in the options array. Most importantly, the options array can include or must include the IP address and port address of the entries offering the service or wanting to subscribe to the service. Also, options for load balancing and other things are available.